Alright, this set of videos is to teach some of those reactions for alkenes and alkynes, maybe just a review for you if you're using it that way. But first off, we have this hydrogenation, right? All you need to do is add hydrogen across that double bond, and you end up making an alkane from your original alkene. Right, so just add hydrogen across that double bond. The double bond just disappears. You have the same amount of carbons. I went from a 2-butene to a butane product. So this one should be pretty easy. The only time it's a little bit different is if I have more than one double bond. Then I can add multiple hydrogens across both of those double bonds and still just end up with the same number of carbons, get rid of the double bonds. Alright, it also works for alkynes. If I had a triple bond in there, as long as I have 2 hydrogens to add across both of those extra bonds, I should be able to turn this alkyne into an alkane with 4 carbons in it. So, fairly simple, just an easy jumping point. You're adding that hydrogen across the double bond, right? Breaking this bond, breaking this bond, and making a new bond between the carbons and the hydrogens so that you have your alkane. Halogenation. Similar, except this time I'm actually adding a halogen across that double bond. So I need to actually draw those in my product, whereas I didn't draw the hydrogens on that last slide because I don't have to draw hydrogens. I can always assume that they're there. But I'm just going to break those bonds, add halogens to each side, and you end up with a product that looks like this. Right? So I went from that 2-butene again to that alkane with a couple halogens connected to it, one from each side, each carbon that was originally in that double bond. Okay, so remember X is just generic. It can be a lot of different things. If I have this example, I'm going to add fluorine across that double bond. So all I need to do is redraw 5 carbons, and off of each of those carbons that was originally in that double bond, there should be 1 fluorine. Alright, so no surprise here, still pretty easy. This could be any halogen, whether it's chlorine, fluorine, bromine, iodine, whatever. Just to add 1 to each side, break that double bond. Hydration, though, is a little bit different. Hydration, you have an asymmetrical adding group. You're going to add a hydrogen to one side, but you're going to add a hydroxyl group to the other. So again, we go through the same processes as before. We're going to break this bond. You're going to break this bond. You're going to make a new bond that brings in this new group, that hydroxyl group that's different than the hydrogen that was added to the other side. Again, I don't have to draw hydrogens if I don't want to. I can assume that it's there, so I'm just going to draw the hydroxyl group in this case. But you can see that now that I have this asymmetrical adding group, I can get multiple options. Right? I could have added that hydroxyl group to the right like I did, or I could add it to the left. In this case, one versus the other, they're actually the same thing. So I don't want to draw 2 products here. But if I have an asymmetrical alkene from the get-go, then I should end up with 2 different products. because adding to one side or the other does make a difference. So I could end up with a hydroxyl group here, or I could end up with a hydroxyl group there. So you can get two different products, obviously not if it's symmetrical like that first example, but if it is asymmetrical from the get-go, if you can look across this double bond and this side's the same as this side, you're going to get one product. But if you look across this double bond and this ethyl group here is different than this methyl group over here, then it is different. It is going to matter which side you put that hydroxyl group on. You are going to get two different products. So you're just looking for symmetry or asymmetry. If it's symmetrical, you get one product. If it's asymmetrical, you can get two. That being said, there's also a new rule that we're going to have to worry about for these, because it turns out, even though you might think that there's going to be two products, that's not always going to be the case. And it's just something we're going to have to deal with. Right? If I added that water across this double bond in this molecule, this is a 2-methyl 2-butene. In theory, I could get two different products. I could have the hydroxyl group here, or I could add the hydroxyl group over here. Right? Each of those original carbons in that were part of that original double bond. Remember, this is asymmetrical. I could get two different products. Those are different from each other. But it turns out, if you do this in the lab, you're only ever going to get one of these products. This product over here on the right never ever is formed. And that's where Markovnikov's rule comes into play. We found out that looking at those carbons in your double bond, if one side of that double bond has more hydrogens than the other, then that's the side that you have to add your new hydrogen to, whereas the hydroxyl group is going to go to the other side. So Markovnikov's rule says that if one side has more hydrogens already, that's where the hydrogen needs to be added from that addition group, that adding group. Right, so remember, I was adding a hydrogen to one side, a hydroxyl group to the other. You need to add your new hydrogen where there's already more hydrogens. I drew that a little funny. I remember there's an original hydrogen here. And then I'm going to try and add this group across that double bond. So I'll break this bond. Oops. Break this bond. Reform new bonds between that hydroxyl group and the carbon on the left and that hydrogen and that carbon on the right. I'm always going to get this product, though, not the other one, because of this rule. See the other way that Markovnikov's rule applies, right? I can add a water across this double bond, but again, only one product is ever formed. It looks like you can make two, but only one should be formed. You're supposed to check. This side already has two hydrogens on it. This side only has one. So I'm going to add that hydroxyl group to the side that had less hydrogens to begin with, making this side over here have three hydrogens that I don't necessarily have to draw. But the one with more hydrogens already ends up with even more hydrogens in your product. That's how you're supposed to predict which one is formed. Okay, notice that this only mattered if this was asymmetrical to begin with. So we have to go back to that idea before. If you had a symmetrical alkene to begin with, right? When you're adding to one side or the other, it doesn't make a difference. You're still going to get one product, but Markovnikov's rule wouldn't have made a difference either here, because there's one hydrogen here, there's one hydrogen here. Neither side has more hydrogens. You're only going to get one product. And it doesn't matter which side you add it to, it'd be the same product either way. So our original example, you only got one product because it was symmetrical to begin with. Okay, so that brings us to hydrohalogenation. Again, I have an asymmetrical adding group. I'm going to add a hydrogen to one side and a halogen to the other side. Generic halogens are X. Eraser's not working here. Oh, I'm trying to do the wrong thing. Break that bond. Break this bond. Connect to either side. This was a symmetrical reactant, so it really doesn't matter which side I add that halogen to, it's going to be the same either way. But again, we have this that Markovnikov's rule that could come into play. So things I want you to think about. Is it symmetrical? Because if that original alkene is symmetrical, you're only ever going to get one product, no matter what. So if you can answer that question with a yes, then you're going to get one product. If your answer is no, you might get two products, but you got to ask another question. Does Markovnikov's rule matter or not? Because if Markovnikov's rule matters, then you're only going to get one product. If Markovnikov's rule does not matter, then you can finally get two products. The only way you can ever get two products is if it's asymmetrical to begin with, and Markovnikov's rule matters. So you kind of go through that series of questions, right? If it's symmetrical from the beginning, you don't have to worry about Markovnikov's rule. You're only going to get one product. But if it's asymmetrical, you may have to worry about Markovnikov's rule. So again, an example could look like this. And this is obviously asymmetrical, so I could get two products. But I got to look at Markovnikov's rule. So this time I'm just going to add hydrochloric acid across that double bond. But which side should the hydrogen go to? If I look at this carbon here, there's 0 hydrogens on it. There's already 4 bonds on that carbon. This carbon over here, though, has 2 hydrogens. You always add your hydrogen to the side that already has more hydrogens, meaning this is the only product that I could make in this example. Add that chlorine to the carbon on the left. So that's my product. Okay, so that's hydrohalogenation. It's the same as hydration. You just have a halogen instead of a hydroxyl group in your product. Okay, so that brings us to a new thing that we might have to worry about, right? If there's a triple bond and you're trying to add an asymmetrical group across those existing bonds, it's really kind of a two-step process. I'm going to take one of these adding groups and add it across here. It really wouldn't matter which side or which way I add this, because again, remember, this is symmetrical right now. So I'm going to break those bonds. I'm going to connect here and here. I'm going to start out by getting this product. But now when I try and add in another hydrohalogen, now it does matter which side that X goes to, which side that halogen goes to. And if you have been following along, you know where to put it. The carbon on the left right now has 2 hydrogens. The carbon on the right only has 1. So if I'm going to add this hydrohalogen, I have to add the hydrogen to the left, because that's the side that already has more hydrogens. Right, I forgot that was generic, not a chlorine. So again, I'm going to break this bond here, break this bond here. I'm going to make some new connections here and here. But my final product has 2 halogens attached to the same carbon. And that always happens, no matter what. So the reason why that would matter is if I had this situation, make that a little long there. Let's say I have this alkyne. Right? When I'm adding across that initial double bond, there are 2 different ways that I could do this. I could end up adding the halogen to this side. Right? Remember, I'm adding 2 of those hydrohalogens. I do have a catalyst here that's necessary. But I can add that first one the way that I just drew it on the right, or I could have added it to the left, and those would be different technically, because that was asymmetrical from the beginning. But when I add the second halogen to each of those, it's going to have to go to the same carbon that already had a halogen, which was that carbon number 3. I drew this a little differently because I didn't have a double bond anymore. But both halogens always go to the same side. But that doesn't mean you can only get one product. Because at the end of the day here, I can make 2 different products. One has both halogens on the 3 carbon in the middle, the other has both halogens on the 2 carbon, and they are different from each other, so that's a possibility. Okay, so we just got a couple more reactions left. Hydroxylation. When you see this, when you see that mild ox reactant, this one's fairly easy. All you have to do again is break your double bond. So I'm going to break this double bond here. And always, if you see that mild ox, each of those carbons from the original double bond is going to end up with a hydroxyl group. So again, this is not an asymmetrical thing. You're only ever going to get one product. You just have to know to add hydroxyl groups to both sides. So break your double bond, add hydroxyl groups. So whether it was that original reactant, or maybe this one here, as long as you have that mild oxidizing agent as a catalyst, you just need to break your double bond, and each of those carbons that was part of that original double bond needs to have a hydroxyl group on it, and that's going to be your product. So So this one's fairly simple. You just have to remember to do that when you see that catalyst. This one's a little bit more difficult because in oxidative cleavage, you're actually going to cut this whole molecule in half. And if you have a strong oxidizing agent, I'm not just going to break one of these bonds. I'm actually going to break both of those bonds and cut this thing in half, more or less. So remember that original molecule there has 4 carbons in it, 2 here, 2 over here, since I'm splitting it in half. But each of those original carbons that was part of that double bond is now going to have a double bond to an oxygen on them instead of being connected to each other. They're each connected to an oxygen. So you split it into 2 different pieces. So when this is going to be the hardest is when I start drawing something that looks kind of crazy, kind of funny. Sometimes it's hard to tell what to do with it. But really, make it easy for yourself. Just split that double bond. Remember, I need my catalyst here, so I'll draw that in quickly. You just need to split that double bond, cut it in half. I'll take one of those pieces, that top part, and I'm going to have a double bond to oxygen where that original double bond was. And then that other piece also has a double bond to oxygen, but they're separate from each other now. You got 2 different products there. One of the hardest examples of those that most people struggle with is if I have a ring to begin with, and I have that double bond between 2 of those carbons, and I have that strong oxidizing agent. You're supposed to break that double bond, but now this is no longer a ring, and you got to recognize what's going on here. And if I break that double bond, this is no longer a ring. So instead of going 1, 2 like I would have originally, I'm now 1, 2, 3, 4, 5, 6. So make a hydrocarbon chain with 6 carbons in it, and off of each end, off the 1 and off of the 6, there should be a double bond to oxygen. So if you can make that product, you should be good, but you got to recognize that you're breaking that ring. You still have to see how many carbons are there. You still need the same amount of carbons, but you technically don't get 2 different products in this example. You just get the 1, right? It was still connected the other way around. You just disconnected that 1 and 6 carbon that were originally your 1 and 2. So these 2 products from before, you had 2 different products because you broke that molecule in half. If you only break a ring in one place, it's still all connected some way, somehow. You're only going to get 1 product in that case. Okay, and finally, the last reaction that we have to go through is actually one of the simplest. If you're going to make a polymer out of ethene, right, 2 carbons with a double bond, you're going to do it something like this. I'll start out with just 2 of those ethenes. There's 4 of them total. But all you need to do is break this bond here and reform a new bond here, and now those 2 things are connected. You took 2 molecules and now it's 1. If I take another ethene, I can do the same thing here, break this bond, make a new connection from here to here, and you can just keep adding to this growing chain as many ethenes as are available, you can add. But what you should see here is that at the end, I had 4 ethenes that I put together, so I should have 8 carbons in this chain. So it's 1, 2, 3, 4, 5, 6, 7, 8. So although I could go through the process of drawing and breaking bonds and redrawing new bonds, what I really need to be able to do at the end of the day is if I have a certain amount of ethenes to begin with, say 5 of those, and I have my polymer catalyst, all I have to do is end up with 10 carbons. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But the one thing you have to remember to do is there's always going to be a double bond on the end. I still had a double bond here because there was no new ethene to add to there, but you're always going to end up with one double bond on the end of your final product. So remember, 5 ethenes, there's 2 carbons in there, so there's 10 carbons on this side. So I have a decane drawn over here. 1, 2, 4, 6, 9, 10, with a double bond at the end between the 9 and the 10, and that's your product. So the biggest thing you're looking for is what number is here, because that's going to tell you how long your chain is, but otherwise just make sure there's a double bond at the end and you'll have your product, you'll have your polymer. Okay, so those are all of our reactions for alkenes and alkynes. We're going to have more later this chapter for aromatic hydrocarbons. For those things are different, so we'll get to that when we get to it. But this is good for right now. Hopefully it can help you get caught up.